Exercise 1H Applications. Today we are practicing critical thinking skills through application problems. What you need to be able to do is break down worded problems to understand what is required, recognize the various steps to complete a worded problem, and then find solutions based on the question's requirements. So starting with example 34, what you'll notice that these examples are from the textbook as well. So if you want to refer to it, I'll just be basically going through those. So this one says a rectangular piece of cardboard has dimensions by 18 centimeters by 24 centimeters. Four squares, each x centimeters by x centimeters, are cut from the corners. An open box is formed by folding up the flaps. Find a function v which gives the volume of the box in terms of x and state the domain of the function. I just want to note before I start going through this example that the applications, the idea of it is that every single question is different and you could totally get something you've never seen before. And all you have to do is apply your knowledge to something that's a brand new scenario. Now, this one's actually quite a familiar problem to you. So we have done questions like this before, but in our next example, it might be something unfamiliar. I would suggest that you try to do every question in your applications just to try to expose yourself to as many application problems as you can. All right, so as we said, though, this one hopefully should be quite familiar. So if we try, whoops, accidentally slided through. If we try to visualize what's going on here, we can see that we've got a net here. And what we're actually doing is we're cutting out these sides. And once we cut them, we're actually folding up the flaps like this. So if you try to think about it in terms of in a 3D sense, what's happening, the box has been flipped upwards and the box at the top is open and it'll look something like this. Right, so these sides have all been flipped up. These are the length X, and it's formed an open box here. Now, in terms of the other sides, you can see that this one, for example, is 18 centimeters, but then I need to subtract 1x from here and 1x from there. So all that's left that we can see is this side that I've just crossed. So that will be 18 minus 2x's. And then the same goes for the other side, 24 minus 2x, because all that we can see is this part that's left over. The other x's we've already crossed out. All right, I'm just going to remove all of these so that's a much nicer and obvious diagram. Okay, so that's the box, that's visualizing what's happened. Now what it's asking us to do is to find the function v, which gives us the volume of the box, and also for us to state the domain. So let's just start off with the function v, which is the volume. Now the volume of any box is length times width times height. So all I have to do is just multiply all of the dimensions that I can see. It doesn't really matter what order you put it in. So x is the height, then we'll have 18 minus 2x and 24 minus 2x. Now you can technically leave it like this, but it's actually really nice if you can factorize and simplify it further. What I can see is that there's a factor of 2 in both of these brackets that I can remove. So if I remove a factor of 2 from the whole thing, I end up removing a total of times 4 because 2 times 2 is 4. So it'll be 4x, and then I just divide everything in the brackets through by 2. So it'll be 9 minus x and 12 minus x. Okay, and that there will define your volume. All right, that's the first part of the question done. The next part is about the domain. So there's two ways to do this. The first way is looking at the dimensions, and the second way is sketching. Really, to be able to understand what it is that we're looking for, we should look at the dimensions of the box, and then I'll show you how to just quickly do it by sketching the graph so that you can visualize it in the future. All right, now the idea of the domain is that all of the dimensions of the box needs to be positive. You can't have a negative width, a negative height, or a negative length. So our three dimensions, which are listed here on the side, x, 18 minus 2x, 24 minus 2x, needs to all be positive. So we can say x is greater than or equal to 0. Now, the equal to part, some textbooks include it, some textbooks don't. Cambridge, which is the one that we're working off, does. So that's why I'm including it today. Technically, you can have a width or a height of 0, and it just results in a volume of 0. But we certainly can't have anything that's negative. So that's our first dimension. It tells us that x needs to be greater than 0. That's great. Hopefully super obvious. All right, let's try the next one. So the next one, which would be the width, 18 minus 2x needs to be greater than 0. That needs to be positive. So if I take it over and divide by 2, I end up getting that 9, or rather x needs to be less than 9. Now, if you think about it, if x was any greater than 9, say I put in 10, so 2 times 10 is 20, 18 minus 20 gives me a negative dimension. So that's why, as long as x is less than 9, I'll end up with a positive dimension there. All right, we'll do the same for the last one. So that'll be 24 minus 2x greater than or equal to 0. Same thing, if I take that over and divide by 2, I get x needs to be less than or equal to 12. Now, this is very interesting because this one's saying less than 9, this one's saying less than 12. Which one do we take? Well, the answer is that you always take the one that is more restrictive. So, for example, as we saw before, when I substituted in 10, I got a -2. If I substitute 10 in here, it'll be fine. So 2 times 10 is 20, 24 minus 20, 20 will give me 4. That's all good, but it doesn't work here. So we need values that will work for every single one, which is why we always take the most restrictive one. So this tells me that x needs to be greater than 0, but less than 9. Now, you might be able to just kind of look at the function here and be able to tell straight away. So that's 0, 9, 12. That tells us that it's between 0 to 9. Obviously, this is the longer way, but it is important for you to understand why we do what we do. All right. Now, the next way you can do it is to sketch. Again, that can just come off of being able to look at the function and visualize it. So it is quick to do it, but I just wanted to do that first way to ensure that you understood why we are doing what we're doing. All right, now if I were to sketch this function, I can see I've got 3 intercepts, one at 0, one at 9, one at 12, and it's a positive cubic. So it's going to look like this. So in general, the domain for any function like this is always the first positive section, which we can see straight away is between 0 to 9. I know that this also gives me a positive volume, but as soon as you've crossed over that 0, it won't work. The reason that this gives you a positive volume is because if you substitute in this x value, say it's 13, if we sub in 13 into either of these, so if I put in, I can even just put it into here, 9 minus 13, I'll properly write it down just to visualize it. 9 minus 13 gives me -4. 12 minus 13 gives me -1. -4 times -1 is +4. So that's why it results in a technically positive volume, but the dimensions themselves are negative. So it's false at that point. So as soon as you cross your first intercept, that's it. You can't anymore. Nothing after this is going to work. Okay, so that's how you can go about solving this problem with two different ways to find the domain. On to our last problems for today. That's example 35. What we are going to do is we've got a rectangle. It's inscribed in an isosceles triangle with dimensions as shown. Find an area of rectangle function and state the domain. So what we're looking for is this area here. And this one's going to be very interesting. It's a question that you might not have seen before. So this is what I was talking about, trying out different things, trying out as many questions as you can to expose yourself. All right. Now, we want an area for the rectangle. We know that the area of a rectangle is length times width. That's great, but I can't actually tell what the length and the width is. So I'm just going to give it some variables. I'm going to call the height y, and I'm going to call the width of it 2x. Now, the reason I'm calling it 2x instead of x is because I know where this question is going to go, and it's going to result in fractions if I don't call it 2x. Now, once you have practiced enough questions, you will also know where you need to go. Or you can get to a point where if you did get fractions, then you can go back and change it. So I don't want to deal with fractions. That's why I'm going to call it 2x instead of 1x. So the area of this rectangle is 2xy. Obviously, this is an issue because we can't have an x and a y in our function. So I now need to find an expression for y that includes x. So I need to find a relationship between x and y. You might stare at this for quite a bit, but what you'll notice eventually is that actually you need to use a technique of similar triangles to be able to solve this kind of problems. Now, I'm going to show you where the similar triangles are. So our first similar triangle is going to be this large one over here. And then our second similar triangle will be this little one over here. So you can see that these two triangles have got the exact same angles. So these ones literally have the same angle. They've both got a 90-degree angle. And because two of the angles are the same, that implies that the third angle will be the same. And the idea of similar triangles is that because their angles are the same, then they will grow in proportion. So their ratios of the lengths are going to be in the same proportion and ratio. So from that, we can actually start to come up with some values and start to get a relationship between x and y. All right, so if I were to write what I have so far for our little triangle, I can see that the base of this is x. I don't know anything else yet, but I can kind of see that this is going to be the whole height of the rectangle. And minus the y, which will give me this part here, which is the x. So what I need to do is find the whole height of this triangle and minus y, that'll give me this part here. To be able to find it, I need it anyway for this triangle. We can use Pythagoras. So this side is 15. This will be half of it, which will be 9. And then to find that last side, I can use Pythagoras. So that'll be 15 squared minus 9 squared is equal to 144. And take the square root of that, that'll give me 12. So if this whole thing is 12, and then we've got the y that's left over here, that means I will have 12 minus y for this section. Okay, so now that I've got my two similar triangles, remember it's all about the ratios, they're the same proportion, I can now compare sides. So that means I can compare these two sides here and these two sides here. So x divided by 9, so the ratio between x and 9 should be the same ratio between 12 minus y and 12 because they are similar triangles. Now remember what the whole point of this is, to get y by itself so we can substitute it into the original equation. So I'm going to go ahead and rearrange. So that'll be 12x on 9 is equal to 12 minus y. And then I'm just going to flip them. So I'll get 12 minus 12x on 9. All right, now that I have an expression for y, I can go back to my area equation. And instead of writing y, I can write 12 minus 12x on 9. And again, it's just nice to be able to simplify it by factorizing. So I can factorize 12 out. So that'll give me 24x. Divide everything by 12. So that'll be minus x on 9. All right. Now, if you want to make it look a little bit nicer, what you can also do is you can actually remove 1/9 from. So the fraction ends up on the outside rather than the inside. You totally don't have to do this, but it just makes it look better. The way you work out what is left over, so 1 divided by 1/9 will actually give you 9. And then you'll just have an x there, which is quite nice. Okay, so that there is your area of the rectangle. Now, the last thing it's asking for is the domain. So what is the domain here? You can do the same thing, which is sketching. You can do the thing with the dimensions, whatever you want to do. If we were to quickly sketch it, because I do think that's the easiest way to do it, we can see that this is a negative quadratic with an intercept at 0. That's the first part, 24x on 9, and an intercept of 9. And remember, the domain is just going to be your positive section there. So x would be an element between 0 and 9. All right, so that's it for your applications exercise. Please do go ahead and practice as much as you can. See you next time.